We now want to look at another type of distribution, the actual binomial distribution. It's still a discrete distribution, but it's like what we were looking at yesterday with binomial probability. We repeat that Bernoulli trial over and over again. So x will represent the random variable denoting whatever it is we're looking for, whatever the successful outcome is that we're interested in. And this is what we saw yesterday. So basically it's exactly the same as how we would work out binomial probability. Probability of success to the power of x, therefore probability of failure to the power of n minus x, and then we multiply by the binomial coefficient ncx. Well, let's now work out some data. If we were to go and plot every possibility and get our lovely distribution curve, here's the table. So when x is 0, we get nc0, p to the power of 0, q to the power of n. When x is 1, we get nc1, p to the power of 1, q to the power of n minus 1, and so on and so on and so on. We know they're all going to add up to be 1 because what we're basically saying is it's the expansion of p plus q to the power of n. But p and q is the probability of a success plus the probability of failure, which we know adds up to be 1, so 1 to the power of n must be 1. So they certainly all add up to be 1. If we look at our row, our xpx, okay, we'll now go multiply each of those by x. And then also, to work out variance, we're going to need x squared px. So there's that particular row. So expected value will be the sum of that xpx row. And we get this expression here. So I want to play around with this expression. Well, first thing I'm going to do is pull out that first term when k equals 0. Because that is just going to be 0. If you sub 0 into that, I'm going to get 0 times nc0 and so on. So really, I've now just got this sum, k equals 1 to n, of that expression. But I'm going to rewrite it like so. Now, it might not be obvious, so let me just write it up here, why that is indeed the same. So what have I got? I've got k times nck, but remember nck is n factorial on k factorial n minus k factorial. Have a look at how I've rewritten it like so. Well, what I've done then is I've factorised out the n, so the top becomes n minus 1 factorial. But the other thing I've done is I've cancelled the k into the k factorial, which makes that k minus 1 factorial n minus k factorial. But if you now look at the two terms on the bottom, they do indeed add up to give n minus 1. So what I've got there is n times n minus 1 c k minus 1. So that's how I went from the second line there to the third line. All right. Well, n is just a constant number, so I can pull that out of the sum. But I'm also going to pull out of the sum just one of the p's, because p is that probability, it's a constant. Bang, pull it out. Which means the expression now is this: n minus 1 c k minus 1, p to the power of k minus 1, q to the power of n minus k. It's actually in the exact same form as our binomial probability. And if I play around with that, instead of going from 1 to n, if I replace k minus 1 with k, so everywhere I see k minus 1, I'm going to replace it with k, I can rewrite that sum like so. It ends up being k equals 0 to n minus 1 of k, n minus 1 c k, p to the power of k, q to the n minus k minus 1. And that is p plus q to the power of n minus 1, which we know is equal to 1. And we just get a very simple formula, np, n times p. Variance, there's a bit more manipulation for this one. Okay, expected value of x squared minus the expected value of x squared. I'm going to play around with x squared and rewrite that as x times x minus 1 plus x. The other thing with expected values, I can break up the sums. So now I've written it as expected value of x, x minus 1, plus the expected value of x, which we just said was np, and then minus the n squared p squared. So let's have a look at this expected value and play around with that. The expected value of x, x minus 1. Well, that'll be k, k minus 1, nck, p to the power of k, q to the power of n minus k. And just like I did with the other one, if I pull out the terms that I know are going to equal 0, and in this case it would be when k equals 0, because that would make k equals 0 there, but also when k equals 1, because 1 minus 1 would be 0. So I pulled up both of those terms, and I'm left with this sum, k equals 2 to n, which, similar to what I did before, playing around with the factorials, I could show is the same as this. I can pull out the n minus 1. This time I'm going to pull out p squared to leave me with this expression, which then I rewrite again. I'll make it k equals 0 to n minus 2, and that becomes p plus q to the n minus 2, which we know is equal to 1, and we end up with this, n minus 1 p squared. So let's sub that back into the variance, because that's what we were trying to work out. We now know that's n minus 1 p squared. Look at that beautiful expression. It's just simply npq. Now, so all you really need to know is those two simple little formulas. So what do we know? If we have a binomial distribution, there are two important things we want to know. How many times we're doing it, so that's n. And what's the probability of success? That's p. They're the two key pieces of information. And if we've got that, we know the expected value would be n times p. If you think about it, makes sense. Because if the probability of success is p, and we're doing it n times, then I would expect to get n times p. Because every single time I would expect to get p. So I've got n of them. The variance becomes np 1 minus p. If the probability of a binomial distribution is less than a half, we should end up, well not should, we will. We will end up with a distribution that is positive skewed. If it's equal to half, so everything was equally likely, then we get a beautiful symmetric curve. And if it's greater than a half, we'd get a negative skewed curve. So we're going to have a look at some different situations and work out, could this be a binomial distribution? Could we use a binomial distribution for this? And if it is, then we'll define the variable and state the different parameters that we want. So here's the first one. We've got a normal dice. We're going to roll it 10 times. Find the probability of getting 3 4s, 3 5s, and 3 6s. No. You could not model that with a binomial distribution because there are 3 different things that you're interested in. Remember, the binomial was simply, we're going to investigate something and whether it's successful or whether it's not. So no, that one we can't do. Okay? Now, if the question was just simply, what's the probability of 3 4s, then that would be binomial. Because we could define our random variable. What is the thing we're interested in? Okay, the number of 4s is what we're interested in. We could do that. Or similarly, if it was simply how many 5s or how many 6s. Yeah, we're going to toss a coin and we're going to keep tossing it until we get a head. What's the probability that 8 tosses are necessary? Now again, this one would not be binomial because we don't know how many trials there are. So we don't know. Our binomial distribution, remember the 2 key pieces of information, we need to know how many events there are and the probability of success, and we don't have that. So, no good. Jar's got 49 balls, numbered 1 to 49. 6 of the balls are selected at random. Probability that 4 of the 6 have an even score. Now this one here really depends. Are we putting the balls back in? Or are we not? Remember, binomial probability had to be with replacement. So it really just depends. So if it's not replacement, then no, it couldn't be binomial because the probability will change each time you pull a ball out. But if it is with replacement, then yes, we could model this with a binomial distribution. Our random variable would simply be, well, the number of balls with an even score. That's what we're interested in. And we know the 2 key pieces of information. N is 6, because we said we're going to pull out 6 balls. We know how many times we're doing it. And the probability of success, Well, there are 24 even numbers from 1 to 49, so it will be 24 on 49. So we know the two key pieces of information. The actual probability we could work out. Probability that x was equal to 4, our binomial probability, so probability of success to the power of 4, probability of failure squared, times by the binomial coefficients, and to 4 decimal places we get 0.2247. Let's have a look at this example. We're doing something 3 times. The probability of x, whatever x happens to be, they're giving us that in our distribution table. Find the probability of success at 1 trial. Okay, so what do we know? We know how many times it's happening, 3. We don't know the probability of success. That's what we're attempting to find. But we do know these 4 pieces of information. Now, it probably makes sense to use the one where x equals 3. That's probably going to be the easiest one to use. I mean, I could use any of them, but let's go for the easiest one, because probability of x equals 3 will simply end up just being p cubed when we sub in. So we say p cubed is 0.027, so p must be 0.3. There's our probability of success. So what is the variance? Well, that's n times p times q, for want of a better word there. Success times failure. So 3 times 0.3 times 0.7, 0.63. Okay, here's 3 distributions. Which ones are positively skewed, which one's negatively skewed, and which one's symmetric? Well, the first one, nice symmetric. Remember, it's the reverse to logic. That one there, when the thing is pushed over to the positives, that's negatively skewed, and when it's pushed to the negatives, that's positively skewed. Now that's those 3 graphs. Now, which one of these would have an individual trial where the probability of success is greater than pi on 5? All right, well, we have to work out, is that number greater than a half or less than a half? It's certainly not a half. Pi is 3.14 over 5. That's going to give me something bigger than a half. So bigger than a half, I'm looking for something that's negatively skewed. So it's over here. I suppose when you look at these 3 graphs side by side, we can sort of see why. Because if the probability was a half, we get the nice symmetric one. So if the probability is greater than a half, well, it's going to push the probabilities to the right. But if it was less than a half, it'll push them to the left. So B is the one we're looking for. Here's our binomial distribution. The number of trials is 150. Probability of success is 2 in 5. What is the mean and the standard deviation of this? Okay, well, the mean is same as expected value. So n times p, we get 60. We can find the variance, and once we've got the variance, we can work out the deviation. So n times p times q, we get 36. So our deviation there is 6. How many more trials would we need if we wanted that average, that mean, to rise to 100? So what we're now saying is, well, actually, we would like the answer to be 100. It's n we're trying to work out. N's 250. Make sure you answer the question though. The question is not saying how many trials do you need all up, it's saying how many more trials do we need. We've already done 150 trials, so another 100 would be needed. But what effect does that have on the standard deviation and the overall distribution of the data? Well, our deviation now becomes the square root of 60, which is roughly 7.75. So our deviation has increased. It's got bigger. Well, if it's got bigger, that means our data is more spread out. And that's what it's saying. Our data now is going to move away from the mean. It's going to be more spread out. Okay. We have an experiment. I'm going to roll 2 dice. I'm going to do it 10 times. And the number of times the sum equals 7 is noted. 7, of course, is the highest probability when you roll 2 dice. Find the mean and standard deviation of that distribution. Okay, so we're interested in looking at the number of times these 2 dice come out to be 7. We're doing it 10 times. Probability of success is, well, 6 and 36, which simplifies down to be 1 on 6. There's our mean, n times p, to 2 decimal places, 1.67. Our variance, but we want deviation, so deviation 1.18. We're going to repeat that experiment 1,000 times. Now I did a simulation on a spreadsheet and there's the data I came up with. Find the mean and standard deviation of this simulation. So it's not that we're rolling the dice 1,000 times, we're actually going to end up rolling the dice 10,000 times, because our experiment is to roll it 10 times, and we're doing that experiment 1,000 times. What we've recorded here is in each of those rolls, how many times did we get no 7s and 1 7 and so on and so on. You'll notice by changing notation here, because theoretically now I'm using experimental probability, and so instead of using mu I use x with a bar on top. Again, probably not a huge deal, but technicality. And again, you'll notice I've got FR there instead of probability of x, because relative frequency we're saying. It's still the same thing though. It's sum of that row, which is 1.633. Instead of using sigma, I've used S. And we end up with, no, we want the deviation, so we want the square root of that, 1.22. Draw both frequency polygons. That's what it ends up looking like. So that theoretical one is the orange one there. My simulation is in the blue. Remember what we saw with relative frequency. The more times you repeat an experiment, the theoretically closer and closer it should get to matching that theoretical data. If you could do it an infinite number of times, you would expect it to be perfect. It's not too bad with just 1,000. It's a little bit lower down, but it fits it pretty good over on the right hand side. It fits it quite well. So 17b, playing with our binomial distribution.